Thank you. This talk is based on the project that I carry out together with Professors Piechocki and Guść and Dr. Plewa. And it's still a work in progress, but I will try to present here what we have achieved so far. Although we are not yet able to answer the question in the title. Since spikes as a concept has already been introduced in the morning session today, I will first just describe what does a spike look like in our conventions and with the parameterization of time that we are using, while in the second part of my talk, I will discuss the quantization procedure that we apply to the considered system using the affine quantization, and I will arrive up to the point at which we have currently stopped. As it was already mentioned, BKL conjecture, according to the BKL conjecture, points of space-time close to a singularity decouple from each other due to spatial derivatives becoming negligible in comparison with the time derivatives. So they evolve, all these points evolve independently, but in some of them they develop sharp features that we call spikes, and they are maybe a bit surprising, therefore interesting to study. In particular, it may be argued that they might act as seeds for the primordial matter inhomogeneities responsible for the generation of structures in the early universe. However, it's still not completely answered whether they survive after we perform the quantization procedure on them, or they are somehow smoothed out. And according to one of the previous studies, it seemed that they actually disappear, but we now try to improve these previous results and perhaps modify them. Also, in particular, taking into account the problem of time. The starting point that we consider is inspired by this paper by Esztekar, Henderson, and Sloan. And there, the gravitational variables are the spatial connection contracted with a densitized triad, as well as extrinsic curvature, also contracted with a densitized triad, and they can be represented as matrices. And in the BKL regime, the independent degrees of freedom contained in these variables actually reduced just to eigenvalues of these two matrices, Ci and Di, where Di is a kind of momentum. And these two sets of variables satisfy the Poisson algebra, which is an affine Lie algebra. And these affine algebras already appeared yesterday or 2 days ago in some talks. Okay, now the Hamiltonian of our system has the following form, and it determines, with the help of Poisson brackets, the equations of motion for these variables C, I, and Di. And we also introduce a scalar field, which is not mixing with the other variables, and which plays the role of time. As we consider together two possibilities that we have plus or minus here, and we reparameterize time by the transformation of variables, changing the time derivative into derivative over phi multiplied by its momentum. Furthermore, we have the constraint condition of the Hamiltonian that it vanishes. And now, in order to make life simpler, we assume specific initial conditions at the initial time phi 0, such that Ci is positive and very small, while di are ordered in such way. And then it turns out, after analyzing our equations, that C2 and C3 quickly vanish, while D2 and D3 are almost constant, and the system becomes effectively one-dimensional with the following equations of motion, where now prime is derivative with respect to phi, and we have the constraint coming from the Hamiltonian. And solving this system of equations, which can be actually done analytically, but with the help of a computer, or maybe even on paper. And I forgot to mention that we have this d plus d minus here, which are just shorthand notation for these expressions. Okay, we find that the solutions of these equations for C1 and D1 have the following form, involving hyperbolic functions, hyperbolic seconds, and arc hyperbolic tangent. And I also introduced this abbreviation for this simple expression, and this is the sine function that is +1 for positive C10 and -1 for negative C10. C10 is the initial value of C1 at the initial time phi 0, while the initial value for D10 has been eliminated with the help of a constraint condition. And also the particular case when C10 is 0 leads to C1 being identically vanishing on the whole range. Okay, so in fact, the initial value of C10 determines the sign of C1. That is, if it's positive, the C1 stays positive. If it's negative, it stays negative. And in between, we have this possibility that it's 0. And therefore, we may set a spatial coordinate, let's say x equal to 0, at the point where this initial condition for C1 is 0. And then choosing some parameterization in terms of this spatial coordinate, we may draw the plots of C1 and D1 in the spatial coordinate close to 0. Here, in particular, I choose this sign kappa being 1, and phi 0 equals 0, and some values of d2, d3, and pi, which are not relevant. And then drawing these two functions for different values of evolution parameters, our time phi, we can observe that how a spike emerges. That is, starting from a red curve, for d1 it becomes this literal spike at 0, while for c1 we have this kind of jump. Another way we could try to visualize this spike solution is to consider a curve defined as a function of two variables c1 and d1 in the parameter x, and then we may calculate the arc length of this curve using the standard definition from the differential geometry, and this is expressed in terms of a first elliptic integral and the second elliptic integral, and some other functions. And we can then also introduce Frenet vectors and define the curvature of this curve and draw and make similar drawing as before, but now in terms of this curvature as a function of the arc length, which is normalized in such a way that for every value of an evolution parameter, it goes just from 0 to 1. And in this way, we can see, again, starting from the red curve, and then orange, green, blue, and black, that in this illustration, the spike has a form, that is, this representation of a spike as a form of two peaks approaching each other, but never merging actually, but becoming closer and closer. And these two peaks actually reflect two inflection points of this curve R. And perhaps in this simple case of spike, one-dimensional spike, it doesn't. It's not more illuminating than presenting these two graphs separately. But if we considered higher dimensional case, it might be useful. Now moving to the quantum theory, we apply the affine quantization procedure to our algebra. That is, we just replace C1 and D1 with C1 and D1 over a hat. And we can represent each pair of operators C1, D1 on the following Hilbert space composed of two parts of square integrable functions over the negative and positive real half-line with the following measure. And then these operators can be represented in the following way, that C1 just similarly as position in the canonical quantum algebra just multiplies the wave function by the spatial coordinate, while this kind of conjugate momentum is acting in a bit different way than usual. That is, we have this additional multiplication here. And furthermore, the affine algebra also generates the corresponding affine group over real numbers. And this group can be represented as unitary operators in the following way. Here we have a logarithm of this and two parameters, which can be interpreted as phase space variables, pi and qi. And then these unitary operators act on wave functions in the following way. That is, C acts in a quite usual way, while D is a dilation, which means that it rescales the coordinate by this value of q. And furthermore, the action, or in general, this operator, in a way, it splits into two parts. That is, for positive q, it acts only on positive values of xi, and for negative ones, it acts only on the negative ones. And in this way, our reducible representation splits into two irreducible representations. Now we also need, in order to define the scalar product and over expressions, we also need a measure on our group, and we can have either a right invariant or a left invariant measure. And here we choose the left invariant one, which has the following form. And now, as it was described yesterday or 2 days ago, we can choose some element of our representation, and using the unitary operators U, generate a family of coherent states. And these coherent states also have this property that they form a non-orthogonal decomposition of the identity operator given by this integral with a normalization factor here. And this is done for every value of I, 1, 2, 3. And the identity operator for the total Hilbert space can be defined as the following tensor product of these individual identity operators. Now, the unitary operators also have to be extended to the total Hilbert space, and this can be done in the straightforward way, since we want to preserve the symmetry of our construction under the perturbation of C1, C2, C3, and D1, D2, D3. And therefore, the action of a tensor product of these three unitary operators on the function defined on the three copies of this Hilbert space is simply the exponent of the sum of this pi xi and the rescaling of every coordinate of phi, and the product of this Heaviside phi-test for every coordinate. And using the decomposition of unity that we have, we can map a given function on the classical phase space into a quantum observable in the following way: that this function is integrated over the affine group using these identity resolutions, with a sum over positive and negative parts corresponding to the positive and negative real half-line. And these operators are self-adjoint if the function f is integrable with our left invariant measure, and they can be also self-adjoint in some other cases, but then it's not it's more difficult to prove this. Now the approach that we try to apply to the problem of time in this case is the following: that we first start by observing that in the classical case the adjoint action of momentum given by the Poisson bracket is such that when we consider the exponent of momentum with some parameter tau and the adjoint action of this exponent, then it's simply as you may verify, it leads to a Taylor series that is phi basically acts just as a derivative over phi, and the exponent simply leads to a translation in the value of phi by this tau, parameter tau. And similarly, for a wave function of our gravitational degrees of freedom, we may first observe that the time parameter phi can be shifted formally by the action of this tilde pi, which is simply a derivative over phi, and by expanding the exponent into series, you can easily check that it just leads to a translation in this parameter phi, which we now interpret as a translation in time. On the other hand, from the point of view of a quantum theory, the time evolution should be performed by the evolution operator, which is the exponent of I tau times the Hamiltonian operator. And we postulate that our evolution operator is composed of two parts. The first one is the unitary operator acting on the spatial dependence of the wave function, while the second part is just the action of this derivative over phi, and then we may compare this form with the expression of I to minus I tau, the Hamiltonian operator. The Hamiltonian can be obtained simply by taking into account our representation of Ci and Di. Since we do not have any products of Ci and Di, there are no operator ordering issues, and we can simply replace all the classical variables with quantum operators. And now, if we take a time derivative over tau at tau equals 0, comparing these two expressions, this one and e to minus I tau, the Hamiltonian, we can observe that this formula, which splits into two parts under the differentiation, when compared with the Hamiltonian, leads to the following identification of the operator W, which is given by this differential operator and some kind of potential term. And the second part is simply this real function of a derivative over phi. And finally, if we assume that our wave function decomposes into two parts, one depending on the spatial variables and the other on the time parameter, we obtain a pair of eigenequations. The first one is quite easy to solve. It has the following solution if lambda is different from kappa over 2, while for lambda equal kappa over 2 it's a bit simpler, while the solution of the second equation seems to require numerical approach, and this is something that we are working on currently. And also we should observe that since in the classical theory we have this constraint that the Hamiltonian vanishes, which we also should impose this constraint in the quantum theory. However, looking just at these eigenfunctions, we find that actually it cannot be done in the strong sense, that is, in this sense that the Hamiltonian acting on a wave function vanishes, but only in the weak sense of the expectation value in a S-state psi. And the previous study that I mentioned at the beginning, with which we should compare our results when we finish this project, is cited here. Okay, thank you.
So I think related to the slide here, you had one term linear in DOE and one quadratic term, so that looks like you're replacing the classical pi squared with pi squared plus pi.
Where?
Yeah, the slide you just had. The bottom line. The classical version of the would be pi plus pi squared, which is not your original kinetic term in the constraint.
Mm-hmm.
So it looks like you have something which, in terms of phi, is like a time Gaussian model.
So you think it's something alarming that we should?
Well, I mean, that might be why you can impose the constraint, because you modified it at this point. So an alternative procedure would be to solve the constraint for pi, taking the square root, and then you should be able to impose it. That's like just like time water, where it is possible to impose the constraint strongly. Did you try that?
I think not yet. Yeah.
Strong constraint? In which sense?
That has an operator.
In this sense?
H psi equal to 0. So that's not just the expectation value, but the full action is 0 in this time water.
It cannot be fulfilled in this case.
Not in this case, no, that would be a different procedure. But just by analogy, time one also has a pi squared, and that, in this case, it is possible to impose the constraints from.
Maybe, but one needs to check procedure.
Good.
Okay, comments, remarks? No, we thank everyone.